When is it usually?
Wouldn't you think of doing like a Saturday?
Why wouldn't it be Saturday?
That's what I would do, because then you give them the whole day to get foo-foo. Yeah. And there's a bunch more skippers tomorrow. Good grief. All these skippers. All right, cool beans. Calculate the change in pH that occurs when a 0.01 mole solid of sodium hydroxide is added to a liter of a buffered solution as described in example 15.2. So we just did 15.2, right? That's my buffered solution. Yes, we're doing buffers. Buffers. So we should have done this one already. So we have our pH was like 7.4 something.
4.7.
Good? Y'all have this pulled up in your packet? So we already calculated the pH of this solution, right? You have it? Where's your notes? Okay. So we have our weak acid and the conjugate, the salt of the conjugate base of the weak acid. We explained how buffers work, how the hydroxide, how if I add a hydrogen ion, it's going to bind to this. If I had a hydroxide ion, it's going to pull one of these hydrogens off. Either way, it's going to moderate the pH. So we're going to work on the equilibrium here. Here's my concentrations. Okay. There's our ice table. We've got our pH. Looks like X is 1.8 times 10 to the minus fifth. H and X happens to be this X. This is a common ion effect. And remember, this 0.5 is coming from the salt, and this 0.5 is coming from the acid. So pH is 4.74. Everybody got that? Y'all follow me on that one? Everybody good? That's where we're at. Now, given that, I want to calculate the change in pH that occurs when 0.01 mole of solid sodium hydroxide is added to a liter of the buffered solution that we just described in example 15.2. Then we're going to compare that change to what happens when I put 0.01 moles of solid sodium hydroxide in 1 liter of water. Now, why did I use 1 liter of water? Because it does what? Makes for what? All right, molarity. What's the formula for molarity? And at the bottom number, so this would be a, what's the molarity? 0.01 molar solution of sodium hydroxide. Y'all follow me? Okay, let's go ahead and answer the first question first. What's the pH of that in water? If that was just in water, if I started out with plain water, the initial pH, if I had 1.0 liter of H2O, the pH would be what? Come on, I got a liter of water. The pH is what?
14.
7. The pH is 7.
I was thinking with.
Okay, now I'm going to add 0.01 moles and make a 0.01 molar solution of sodium hydroxide. Now what's the pH? Be basic. Give me an actual number. We're chemistry here. 12. So if it's 0.01 molar, this is sodium hydroxide. Sodium hydroxide's at what kind of base? Strong. So it completely falls apart. That means I've got 0.1 molar OH minus, okay? That equals a POH of 2, right? 1, 2. Y'all follow me? So the pH equals, what did we decide? 12. If I added 0.01 moles of sodium hydroxide into a 1 liter of water, the pH would move from 7 to 12. That's a pretty big swing. Yes? Yeah, what you got?
So to find the pOH, you just do 10 to the negative 0.01, right? No?
Rewrite this in scientific notation.
14. For pOH, it would be 14 minus the pH.
Okay, that's the concentration. Just rewrite it in scientific notation. I take that 2, and that's the hydroxide concentration. So the pOH equals 2. Okay, pH equals 14 minus pOH, which is how I got a pH at 2, a pH at 12. All right, so you've got this in your head. This is a pretty big deal. If I was needing to make a base for y'all to use in the lab, and I needed something that was a pH of 12, I could do that pretty easily by adding 0.01 moles of sodium hydroxide. Okay. Now I want to see what happens if I add that much base to a solution, a 1 liter solution like we have in example 15.2. We're going to see how big that change is. Remember, the purpose of buffers is to mitigate or lessen a big swing. So this would be a big swing, right? 5 orders of magnitude swing. All right, let's see what happens here. So first of all, a major species in this new solution is going to be what?
H2O.
Good. Let's start with water. Hey, water is going to be in this solution. What else?
Sodium hydroxide. Sodium and.
Sodium and hydroxide. So there's 2 more. Because this is a what kind of base?
Strong.
It's a strong base, so it's going to completely separate. So I've got sodium and hydroxide. What else?
Are we talking about this new solution?
The solution's going to have the buffer in it already.
Acetate.
I'm going to have acetate. Right? And what else? Remember, to make a buffer, I need a weak acid plus the salt of the weak acid. So I also need acetic acid. Good? All right, let's go through these. Got my acetic acid, I got my sodium, I got my acetate, I've got my hydroxide, and I've got water. Okay, so here's my reaction. I've got my hydroxides going to react with a certain amount of acetic acid. This is going to be a neutralization reaction. Notice this hydrogen's still attached. It's going to make water as a liquid, which means we're going to ignore it. And then I'm going to have acetate, aqueous acetate. We okay so far? This is the reaction that I'm actually looking at. So, we're going to make some assumptions in our steps. The first one is this is going to go to completion. That is, all of the sodium hydroxide I put in is going to get used up. All of it's going to get used up. So that means that means I'm going to actually use up 0.01 moles of the acetic acid. Now, the solution started out with 5 moles of acetic acid, right? Or 0.5 moles of acetic acid and 0.5 moles of sodium acetate. And let's see why that matters. So let's set our, here's our stoichiometry, right? So before the reaction, before I put the sodium hydroxide in, I had 0.5 moles of acetic acid, and after I put then I put the hydroxide in before the reaction started, I had 0.01 moles of hydroxide. I let them react completely. I'm going to say that all the hydroxide's used up, so I have 0 of that. I've used up 0.01 moles of the acetic acid. So in this case, I'm starting with 0.49 moles of acetic acid instead of 0.50 moles of acetic acid. Because I've converted 0.01 moles of acetic acid to acetate, I now have an extra 0.01 moles of acetate. Are we following? It's okay. It's very annoying when it does that. All right. So now I'm going to do the math all over again. We're going to do the math just like before. Okay. The dominant equilibrium is going to be the dissociation of the acetic acid. And here's our new rice table, right? So in this case, in the previous example, we were 0.50 minus x, x, and 0.50 plus x. In this example, though, we've converted 0.01 moles of the acetic acid into the acetate. So basically, we've got a little extra acetate and a little less acetic acid. All right. So this is after we've reacted the hydroxide before it goes to completion, before it goes to equilibrium. So now can you take those new numbers, plug them into your mass formulas, and go? Yeah. You know, law of mass action, right? Same thing we've been doing all this time. Because we know what our dissociation constants are, right? Ka. So go ahead and solve for the hydrogen ion concentration and then solve for pH. And then I want you to tell me how that pH compares to the pH initially. How does that swing in pH compare to the swing in pH of just putting it in plain water?
Very giant number. Very small, 0.01.
Yeah, this was, I think in y'all's it was what, for 4.735 and then 4.7, what did your calculator actually say?
4.76210.
Yeah, 762. So we're still looking at something that on a pH is 0.02. Now 0.01 moles of sodium hydroxide is actually quite a bit of sodium hydroxide, right? I mean, it would take neutral water and take it all the way down to a pH of 12. right? So that's a considerable amount of water. I mean, a considerable amount of base there. But with this buffer, we were able to control that swing. Yeah, they finally got the air conditioning on. Like it's been off all day. Good? I still like it. I think I like it. I'm trying to decide. I like it better than last year with the dank, humid, the oppressive humidity, the bad hair day every day.
I think today's the warmest day it's ever been since I was still up in
This is the warmest it's ever been. Okay?
The was always so like steamy. It felt fun.
Yeah, it's nasty. It was a nasty,
Pure science. Oh, that was so nice.
it's a nasty hole.
Like you put your hands on the table.
You know, it'd stick.
And then it would like.
Yeah. What is it up to? Oh yeah, I think it was like 23 earlier. Or no, it was, I guess 21. The tattletale says 21. All right.
Yeah, but then we're like big dogs.
No.
I look like a tall 5th grader.
Tall 5th grader?
Yeah.
Yeah, I agree.
Yeah. Huh?
I'm not.
You're gonna break all the rules.
I'll just build a plexiglass box that I walk around in.
It's got wheels at the bottom.
Yeah.
He's a health teacher who doesn't even wear his mask.
That's because he, no.
I'm not going to be a part of this.
That's probably wise. Since it's all on tape. All right.
Someone's going to come for me, no matter what I say.
So we saw a big swing if I just have water with this nice little buffer, little baby swing.
You go?
Okay. No.
What's your shoe?
Huh?
Was that what golfers say?
Yeah.
What's your shoe the other day?
Like a 125 on the front nine.
Like what? Wait, that was
Roman understands.
I'd like to know.
Yeah, no.
Like the lead in
Exactly.
Yeah.
Yeah.
Really?
It's like negative numbers or something.
Wait.
So like really good golfers, just like, 74 for 18 holes.
I'm not acting about it.
Yeah.
I have 7 for
7?
Yeah.
And not only does it do hole in one, it pops out and goes to the next hole.
Yeah, I just want to go down all the way.
Is it possible to get 18 and 18?
In the theoretical world, it has never happened that I'm aware of, but
Hey,
I did it the other day. You just missed it.
yeah, she
No, if you see him do that, he can't do
all right.
Those guys are pretty good.
So here we go. So buffered solutions are solutions of weak acids or bases containing a common ion. When a strong acid or base is added to a buffered solution, it's best to deal with the stoichiometry of the reaction first. So this is what we just did on our example. We take care of the hydroxide, figure out how that's affecting the reaction first. Okay. So here's a little schematic thing. We start with the original buffered solution. I'm going to add stuff. We'll have a change in pH. How am I going to get there? First, I'm going to do the stoichiometry. I'm going to assume that whatever I'm adding, if I'm adding hydrogen ions, like I could have done that same thing with a strong acid, right? And what I would have done is I would have pulled a little bit of that acetate over to the acetic acid. So I could have put like 0.01 molar hydrochloric acid, right, which would have had a pH of 2, and your final change would have bumped it about 0.02 the other direction. Do you visualize how that would happen? Instead of taking the acetic acid into acetate, it would have taken the acetate into acetic acid. But the first step is to assume that whatever it is I'm putting in there is going to go to completion. And then, after we do that, after you figure out whether or not, in this case, it's moving to acetate or moving to acetic acid, then I just rerun the calculations for the equilibrium. Okay? So, let's think about how a buffered solution works. If I contain a large quantity of weak acid and its conjugate base, when I add some hydroxide, okay, this is what's going on. I'm not sure this is any better than the actual example, but are you getting what's going on? If it's a base, it's taking the hydrogen off of the weak acid, right? If it's an acid, it's creating a little bit more weak acid. You probably need 2 squirts.
What's up?
What is that?
Just pass it around the class. We'll.
What's up? Okay, probably.
Just carry around this.
Well, yeah.
Make sure your breast milk
I love
You never know. You never know.
Exactly.
Opportunity arises at any time.
Yeah.
You just never know. Whatever. Harry could just walk in the door right now,
Yep.
and she would be ready. Notice I didn't use any names, so nobody on video knows who I'm talking about.
Jessica.
All right. So let's go back here to how a buffered solution works. If I add hydroxide, we need to do this. We're going to do the same thing here. However much hydroxide ions I'm adding, I need to take away that many ions, that many of the weak acid, and I need to add that many of the salt, of the conjugate base. Right? Okay. So this is how this works. I can look at these expressions. I can say that Ka, right? Does this make sense? Or I could rewrite this as the hydrogen ion concentration equals the Ka times the concentration of the weak acid divided by the concentration of the weak base. I'm going to recommend you guys think about the way we just did it with the rice table. You're probably less likely to make mistakes that way.
With the rice table?
Uh-huh.
Than this.
Than this. But we're gonna go through this because I have to teach it to you. And as we get a little closer, I'm going to show you some stuff. So, all right. So if I add a small amount and add that, the concentration is going to change just a little bit. And that's what we did. So we had 0.5 molar of the weak acid and 0.5 molar of the salt, right? And so I added 0.01 molar of the strong acid, of the strong base. And really nothing much happened, right? Okay, so we're going to say the hydrogen ion concentration and therefore the pH basically remain constant. Okay, there we go. So this is the same thing. I have already explained this to you, but I'm going to read this for sake of completeness. So if I add protons to the buffered solution, for example, a strong acid, okay, the high affinity for the salt, the conjugate base for that, so again, the acetate by itself will grab that, kind of suck it up like a bounty paper towel and stick to it, right? These two are going to stick to each other. So because of that, basically, these guys are floating around waiting to suck up any protons that happen to be in the neighborhood. And I've got an excess of this salt. So if I throw some more protons in, they get stuck. And if they get stuck, they can't contribute to the pH. All right. So I can do all that. So look, this is where things can get kind of fun. I can say that the pH equals the pKa, in other words, the negative log of the Ka, minus the log of the concentration of the weak acid divided by the concentration of the conjugate base. Y'all following me so far? That's what this is. pH, notice pKa. I can invert this. This is called the Henderson-Hasselbalch Equation. Okay, so I can say that the pH equals the pKa plus the log, and then flip this. So you can do this. You can use this all day long. There literally last night was a discussion on the board about how easily students get confused about using this, and how using a rice table will probably get you as close as you need to worry about. You can feel free to use this if you want to. I'm going to recommend, for the sake of your sanity and complexity of problems, that you simply do the rice table work. It doesn't add that much more time. This isn't a big time saver unless it's something you're doing a lot of. Okay, this is the Henderson-Hasselbalch that you read about in your chapter. So this is saying that pH equals pKa plus log of the base over the acid. This is the equation. If you were comfortable with it, if you did a lot of work with it, if this was something we would do a lot of, if we were in a real college chemistry class, say we were at A&M or UT, and we were basically doing a whole section just covering buffers, yeah, you'd want to bust this out. You're going to run into 2 or 3 questions. The Rice table is going to give you a good enough answer. It's going to give you the same accurate answer. It's just going to take a little bit longer. But it's, sometimes like driving. I don't know if any of y'all taken any trips where it's like, well, if you go up on 45 and you take this exit, you turn left, you're there. Or you can weave and take 16 turns and, it's a minute shorter if you go do that route. And you go, you know what, I'm just going to go this way. Okay. This is the difference between the Rice tables and the Henderson-Hasselbalch.
Or you can just have someone else do it. So you don't have to worry about it.
There. Yeah. Well, some of us don't have limos at our service.
Or you can just have a cat.
Or you can just stay home.
We got my cat. I love the catfish. Yeah, we got my cat.
Cool. All right. So let's look at some conjugate acid-base pair ratios and the pH. So for a particular buffering system, the solutions will have the same pH. So I'm looking at acetic acid and sodium acetate here, and I've got a 3 to 5, and so that's going to give me a 0.6 buffering ratio, and a 0.5 to 0.03 is also 0.6. This just doesn't have as much capacity. In other words, I can't dump as much other strong acids or strong bases into it before something happens. All right, so we can, based on this table, we end up with a pH of 4.52. We have to make some assumptions, and that is the equilibrium concentrations are equal to the initial concentrations. And we're going to let X be the amount of acid that actually dissociates. And it's going to be very small. That's one of the assumptions we have to make. All right, so we have a buffered solution that contains 0.25 molar ammonia with a Kb of 1.8 times 10 to the minus fifth and 0.4 molar ammonium chloride. So calculate the pH of this. First thing I want you to think about is who are going to be my major players? Always going to be what?
Water.
Water. Then I don't see any of that here.
Salt.
What is it?
Salt.
Which is what?
Ammonium chloride.
Ammonium chloride. What happens to this if I throw this in water?
It dissolves.
Dissociates completely. So I'm going to have ammonium and chloride. And what else am I going to have? Ammonia.
Well, yeah.
Mm-hmm. What happens when I throw that in water?
Nothing.
We'll have to talk about that. All right.
Oh, wait, no, I think I know the answer.
Wait.
It's a very weak base.
Yeah, it's a weak base.
No, it's cold.
So I've got ammonia,
That's all I know.
I've got the ammonium ion and the chloride ion, and I've got water. Chloride is a weak base because it's a strong acid. That means at this point, we're looking at this, the chloride, we're just going to kind of say, hey, the chloride goes off to the side, don't worry about it. Water is also a weak acid or base. Again, off to the side, don't worry about it. You okay? Split your cuticle? Okay. There's some hand sanitizer over there. No? You don't want to feel something?
I typically wouldn't mind that.
That's all tingle.
Yeah. I love after a day of construction, you go wash your hands and then you put some hand sanitizer in and you find all your little nicks and cuts you got throughout the day.
Like like underneath the fingernails. Oh, those hurt so bad.
Yeah, I split the cuticles. I'm usually busting my knuckles. I've cut my fingers, usually back here where I don't even notice it until I put the hand sanitizer in.
K, I didn't get the K.
What's that? Oh, it's fantastic.
I didn't get the KD or KA. It's like gloves are important. Gloves are important.
No, you get your hand, you get scars, and then you stop feeling pain, and then you just basically train your brain to ignore pain. Uh-huh.
But when you get pepper and you cut,
Oh, that's delicious.
happened yesterday.
Jalapeno juice. All right, here we go. Here's our dissociation. Here's what's going on. I've got the ammonia is going to combine with water. Notice again, the water's in what? This is a liquid, so what does that mean for my?
Ignore it.
Ignore it, good. And this is going to form the ammonium ion and hydroxide. So on the top, I've got the ammonium ion and hydroxide over ammonia. And this is my Kb at 1.8 times 10 to the minus fifth. Mm-hmm. National Athletic Training Month. It's a commemorative Band-Aid. You just need the one, or are you okay? Okay.
Fingers just bleed a lot for no reason.
Yes.
That's typically not a good
It's
sign.
just like, no, it's bleeding.
I got a lot of nosebleeds. It's just the weather.
It just like bleeds so much.
Yeah. Yeah, one of the things that we're going to find as the masks come off is your sinuses. Your sinuses have been trained to live in a nice moist environment. And so suddenly, even down here, it's going to be dry. And so you're going to have a lot of that, because we've been basically breathing out, breathing in all this moist air. And then now, our masks get all nice and moist. And it's going to breathe up. So as you do that, it's kind of like when you step out of your of the hotel or the condo or whatever, when you're up in the north, or you're up skiing or something, and suddenly that blast, that's what's going to be like for us, even though we're at sea level. So we are going to have to retrain our sinuses, yeah, because your sinuses have spent a year basically going, this is cool, I'm happy. So
Is that a good thing or bad?
it's going to be an adjustment, and for some people it's going to cause trouble. It's going to depend on the person,
Or if like
For me, it's probably going to be a bad thing, because I remember like when I go to New Mexico, like
Yeah.
I sometimes get some really bad nosebleeds.
exactly. That's something you might have to worry about.
Fun.
All right, so here we go. We got our Kb, 1.8 times 10 to the minus fifth. Here's our ice table. Notice my numbers are a little different. 0.25 minus x, and this is 0.40 plus x. And this number, you know where that number comes from versus where that number comes from. Just be aware of where those numbers are actually coming from. And again, we're going to say that this plus x and this minus x are very small. We're going to ignore them. I do recommend you guys go ahead and write the formulas. If you're not going to do an actual rice table here, write the formula out like this and then simplify it before you do your math. That's going to let the reader know. It's also going to remind yourself what's going on. But it's going to let the reader know you actually know what you're doing. You're not just making stuff up. Okay? So after we do our punchy, what do we end up with? What's x?
1.125 times 10 to the negative fifth.
Sounds reasonable to me. So if that's the case, what's the pH? How do I find the pH if I know the concentration of the hydrogen ions?
9.05.
Yep.
This is for hydroxide, right?
Mm-hmm.
Yeah, so 9.05. Oh, like, yeah, that's right, still.
9.05.
Woohoo! Look at y'all. Superstar.
Until I get to the homework.
Right. Hey, I'm just shocked, amazed, and impressed that it's getting done. So
Okay, true.
brilliant.
It's so much easier to get done when, like, swim periods just kind of, like, go home if you have something important to do.
Right.
Like, chemistry.
Yes, that's always an important thing to do. Okay. This solution contains large quantities of ammonium ion and ammonia. Okay. So we can calculate things directly. We can also directly determine it using the dissociation equilibrium for the ammonium ion. So I can actually back up and use the Ka for that. Okay. And I can figure out the Ka because Ka times Kb is Kw, right? So I could calculate the Ka as 5.6 times 10 to the minus 10th. If I wanted to do it that way, I think this is perfectly effective to do it the way we did it, to find the hydroxide and then do your calculations on the 14 minus side of things, right? But you could be asked to do it this way, and it's really easy. It's Kw divided by Kb, and if they give you Ka and you need Kb, you just do it the other way. Okay, and so you can use that. I could actually throw real quickly, but y'all see how fast this works? I didn't have to go through the rice table. But the rice table, I'm hoping you've had so much experience with now that it makes sense. That you can do a rice table really easy. It's not that slow. You don't even have to do it. It doesn't. You don't have to draw the whole thing out. You can do a rice table intellectually. This requires you, number one, to know how to use the equation, to know that I've got to get the pKa. So I've got to take the negative log of the Ka, which means I had to have found the Ka. Okay, and then I'm going to do the log, and I've got to remember it's base over acid. So there's my molarities. And then I've got to subtract out the this number here, right? Because that's going to end up being a negative number. So again, Henderson-Hasselbalch, that way if your general chem teacher 2 years from now asks you why your teacher never taught you, you can say, well, he did, we just didn't use it. All right, here we go. Which of the following will not produce a buffered solution? Make your guess. What does a buffered solution require? What two things does it require? Weak acid and
Strong base. Or really,
the conjugate base. Yeah.
weak acid or weak base and conjugate. Or not, no.
And
Salt.
So weak acid and a conjugate base are the salt of a conjugate base. Okay. So if sodium carbonate reacts with hydrochloric acid, that's going to form what?
Sodium carbonate.
There's my salt.
You'll have
Is there a
carbonic acid.
What do I know about carbonic acid?
So weak acid.
Weak acid. So I'll have the salt and I'll have the weak acid of the salt. So A would work just fine. because I'm going to end up making, I'm going to have CO3 minus 2 plus H2CO3, right? That would make me a nice buffer. Which ones can we eliminate? Okay, so which one of those would not produce a buffered solution?
B.
I chose B, but I think it's E now that I'm looking at it.
Well, if I react these two things, what's going to happen?
NaOH is a strong
Strong what?
base.
Base. So am I going to make, using this, can I make a weak acid?
No.
No. So it is E. Because all these others will react with a carbonate to make me a weak. Okay? Y'all ever use Novocaine? Good stuff. Deeply appreciate that.
Wait, what is this?
You get a hint on what
Yeah, that's the stuff they put into your, they'd have a topical and they usually inject it now. So they'd put the needle in your gum before they start drilling on your teeth.
Oh,
yeah,
that's
I've
what
had
it
that before.
is.
Good stuff.
Wait, they do that?
It's
Yes.
Mom told me it's
I
strong, but no.
deeply appreciate it.
Never had dental work done?
I haven't.
well,
But
I mean, it's
it's
mostly
not-
for filling. I'm pretty sure it's
it's
mostly
the-
for filling things.
I use lactic gas.
Okay.
Yeah.
So-
I got it used for. I got it used in the past, I think.
So I've got a solution that's a weak base Novocaine. I add a solution with a small amount of a salt containing the conjugate acid, whatever this is with H. Which of the following statements will be true?
I was more paying attention on the dental.
Yep. So here's our weak, we got a pH of 11, right? All right, I've got a weak base. I'm going to add a small amount of a salt that contains a conjugate acid.
All right.
So if I'm adding a little bit of acid to it, what's going to happen?
You're just going to decrease.
And what else? So if the pH decreases, the POH increases. Yeah, good. So there we go. Nice D. Good. All right. No, pH, the other, yeah, it's E. Yeah, we said it right. I just pointed to the wrong one. So pH decreases, POH increases. Good. Let's consider a buffered solution with a pH of 4 made with hydrofluoric acid and sodium fluoride. Okay? Which of the following statements is true? All the concentrations are going to refer to an equilibrium concentration. So I've got a pH of 4. I've got a buffered solution. What's going to happen?
Wait, can you go back?
Uh-huh. So y'all got the chart, the question we're going to ask, right? Good? So is the hydrofluoric acid going to be exactly equal to the fluoride ions?
No.
Is the hydrofluoric acid going to be exactly equal to the hydrogen ions?
No.
No. Because, well, this one we can eliminate because why? It's a what? Somebody said it. It's a weak acid, yeah. Okay, so I can go back up there, pH of 4. Is the hydrofluoric acid going to be greater than the number of fluoride ions?
No.
No, because we're going to have excess fluoride ions, right, for the buffer to work, right? I've got to have excess fluoride ions. So E, yeah. Sorry, we skipped right through the D. Right, so I've got to have, in order for the buffers to work, I've got to have excess of whatever that conjugate base is in order to suck up, like the bounty, right, suck up those hydrogen ions that might be added. Okay? All right, so the capacity is the amount of protons or hydroxide ions a buffer can absorb without changing the pH too much. The larger the capacity, the more concentration of buffering components. And this is simply determined by the magnitudes. You probably heard me mention a couple slides ago when they were talking about the ratios, right, that one had more capacity than the other. If you've got a large concentration of this and a large concentration of the conjugate base, if you have that, then you can absorb a lot of material. You can absorb a lot of acid or base. Okay? So let's try this. Let's calculate the change in pH that occurs when 0.01 mole of gaseous hydrogen chloride is added to 1 liter of a solution which contains 5 molar acetic acid and 5 molar sodium acetate. And again, for acetic acid, the Ka is 1.8 times 10 to the minus fifth. Go. And yes, you can use your previous examples to help you out.
It's the same thing.
Yeah, if you just
Sig
click through
figs, it's the same
PowerPoint,
thing.
it's going to be exactly.
Actually, wait, no. Sig
All right.
figs. Oh wait, no, it is still the same thing because it's 1 liter.
There it is. Okay. I have to do the unfreeze thing that I keep forgetting about. All right. All right. So they're going to do it their way with the Henderson-Hasselbalch. Okay. These things are going to be equal to each other. Initial pH is 4.74. We did this exact thing a little bit ago, right? Right? This, we did this, right? Except when we did it, it was what? What was this number? 0.5 and 0.5, right? But notice the ratios are the same. So my pH is going to be the same. It's just with a 5 molar of each, I've got more buffering capacity. All right. So I can do the pKa plus log of 1. Use pK, blah, 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 4.74. Okay, so the pH is 4.74. If you want to, you can use Henderson-Hasselbalch. Again, at this point in the year, I'm going to recommend you stick with rice tables. You can solve it exactly the same way. It works out because all Henderson-Hasselbalch says is, look, we're going to take the pK, dissolution, do the log of these two concentrations. All right. After we add the hydrochloric acid to this, now the major species are what? Well, I've got the hydrogen ions, the chloride ions, right? And in this case, this is going to react to form. This is literally what I told you about a few minutes ago. What they're using this experiment for is to walk through doing this with Henderson-Hasselbalch. Remember we told you, so we added a strong base before, now we're adding a strong acid. So again, we added 0.01 moles of acid. So, right, after the reaction, we used up all the acid. I've converted the acetate to acetic acid. So I've gone from 5.0 molar and 5.0 molar to 4.99 and 5.01. This is going to have an effect on the pH. Is it?
Not by much.
Not by much. Even though, again, with 0.01 molar, that is a pH of 2. That would be a pH of 2 if I was just adding it to plain water. But instead, we punch that all in, again, through Henderson-Hasselbalch. Look at the only effect this has. So after we're done with sig figs, we literally have no change. our buffered solution controlled adding 0.01 molar hydrochloric acid, or 0.01 moles of hydrochloric acid to our solution. Good? Okay. I'm telling you, general chemistry is going to be so easy for you in 2 years if you can remember about half this stuff. But your brain's seen it once. It's going to make it easier to relearn. Oops, there we go. There is no change in the pH when I add 0.01 moles of hydrogen chloride to this solution. This solution has a significant buffering capacity. All right, Friday we are going to have class. I will be recording. I have no idea who's going to show up in 8th period, maybe my juniors, but we'll have class. I'm hoping to wrap up chapter 15, and so 17 will be done in about 2 days.
Why isn't anybody coming to class?
So that is a good question.
I have no idea myself.
So